Okay. Example number 3. Carnot cycle. Okay. We have air is the working medium. Used in a Carnot cycle operating between the temperature limits of 350 Kelvin and 1550 Kelvin. The pressure before and after isothermal compression or 200 kilopascal and 350 kilopascal respectively. The network output of the cycle is 400 kilojoule. Determine letter A, the maximum pressure in the cycle. Letter B, the heat transferred. To air. And then the mass of air. Okay, try to analyze the problem. Okay, for the solution, okay, we have temperature is constant, entropy is constant, temperature is constant, entropy is constant. Value of the temperature, 1550 Kelvin, and then this one is 350 Kelvin. Okay. TS diagram, temperature entropy diagram. Now for the process 2 to 3, process 2 to 3, isentropic expansion process. Then you have T3 over T1 is equal to P3 over P2 raised to K minus 1 over K. The constant value for the K of air is equal to 1.4. Okay, therefore, T3 over T1, and therefore, since P4 over P3 is equal to RE at temperature is constant, V3 equal to V3 over V4 is equal to V2 over V1. V2 over V1 equal to RK temperature is constant. Okay, or that is also equal to P1 over P2. Therefore, we have T3 over T2 is equal to P4 over P1 raised to K minus 1 over K. Then substitute the values. We have 350 over 1,550 Kelvin, equal to 1,000. Okay. P1 is 200 kilopascal. Okay, 200 kilopascal over P1. Okay, 1.4 minus 1 over 1.4. Okay, using this equation, find for the value of your P1. P1 is equal to, okay, for P1, okay, for P1, we have P1 is equal to 200 kilopascal divided by 350 over 1,550 raised to 1.4 over 1.4 minus 1. P1 is equal now to 36,555.5 kilopascal. Now, for the heat transfer to air, but before we can find for the heat transferred, we need to find for the mass of air. Okay, let us try for the heat transferred for letter. Solving for the heat transferred to air. Okay, therefore we have heat added is equal to MR T1 ln P1 over P2. Then we have P4 over P3 is equal to P1 over P2. But P1 is equal to P1 is equal to 200 and then 350. 350 is 350 and then 200. 350 over 200. 200. According, we have P4 over P3 is equal to 1.75. Therefore, your P1 is equal to 1.75 P2. P1 is equal to 1.75 P2, then heat added is equal to MRT1 ln 1.75 P2 over P2. Okay, therefore, this one is equal to MR T1 ln 1.75. Cancel your P2 here. Okay, therefore, we have now the equation of MRT1 ln 1.75 for the heat added. But we don't have the value of your mass. Therefore, we have to look for the value of your mass. Okay, let us use the formula for the mass. For the mass of air, we have network is equal to MR T1 minus T4 ln P1 over P2. Okay, we have the value for the network, which is equal to 400 kilojoule. Okay, we have 400 kilojoule is equal to M. And then the constant value for the gas constant of air is 287 if you're going to use joule per kilogram Kelvin. But we're going to use the kilojoule because we have here the given for the network is in kilojoule. Therefore, kilojoule per kilogram Kelvin. Okay. And then times your T1 is 1,550 minus 550 minus temperature. What is the 350 Kelvin ln P1 over P2 is 1.75 ln 1.75. Okay, now using this equation, okay, we can cancel now kilojoule, then Kelvin for the unit of temperature. Therefore, the mass is 2.08 kilogram. We have now the value of the mass. Okay. Going back to your heat added, we have heat added is equal to MRT1 ln 1.75. Substitute the values. We have M, which is 2.08 kilogram. Then again, for the value of your gas constant of air, we have 0.287 kilojoule per kilogram Kelvin. Okay, kilogram. Okay, and then temperature 1, which is 1,550 Kelvin. Cancel Kelvin. And then ln 1.75. Heat added is equal to. Okay, now for the heat added, we have 517.81 kilojoule. Okay, this one is the value. Okay, let us proceed now for the reverse Carnot cycle. Reverse Carnot cycle. Now, for the reverse Carnot cycle, the reverse Carnot cycle has all the same processes as the Carnot cycle. But the reverse Carnot cycle operates in a counterclockwise direction. Okay. Okay, we have 1 to 4. This one is for the reverse Carnot cycle. Excuse me. Okay, we have 1 to 2. 2 first. 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay, this one is the temperature entropy diagram of a reverse Carnot cycle. Okay, a Carnot refrigerator is used to maintain the temperature of a refrigerated space at a temperature lower than the temperature of the environment. Now, the measure of its performance is called the coefficient of performance. Coefficient of performance, COP. Okay. Coefficient of performance is defined as the ratio of the desired heat transferred to the net energy input required to produce the desired effect. Therefore, we have heat at lower temperature over the net work minus equal to temperature at lower temperature over the higher temperature minus the lower temperature times 100. Okay, so that is in percentage. But sometimes no need to multiply it to 100 unless it is required. Now, for the coefficient of performance for the reverse Carnot, coefficient of performance for the reverse Carnot is greater than COP of the ideal, greater than COP of the actual. Okay, this one is read that as the coefficient of performance for the ideal is greater than the coefficient of performance of the reverse Carnot, but greater than the coefficient of performance of the actual. Okay, example. Okay, example problem. Example. Okay. A refrigerator maintains and cooled space at 2 degrees Celsius. When the ambient air around the refrigerator is 30 degrees Celsius, the refrigerator has a coefficient of performance of 2.5. The recooling in the refrigerated space is 8,500 kilojoule per hour. Letter A, determine the power consumption of the refrigerated and the heat transfer rate to the surroundings, to the surrounding air. And letter B, suppose the refrigerator is replaced with a Carnot refrigerator. Refrigerator, determine its COP. Okay. Okay, now for the solution. Okay, now for the figure. Okay, for the TS diagram, we have 2 degrees Celsius, 30 degrees Celsius, 1, 2, 2, 2, 2, 3, 3, 2, 4. Now, what are the given? Okay, given, we have the COP, coefficient of performance, which is equal to 2.5. 2.5. 8,500 kilojoule per hour. Heat at the lower temperature, 8,500 kilojoule per hour. Then, temperature, high temperature is equal to 30 plus 273 equal to 303 Kelvin. Then, for lower temperature, which is equal to 2 degrees Celsius plus 273 is equal to 275 Kelvin. Now, for the solution, okay, COP is equal to heat at the lower temperature, network is equal to W net is equal to QL over COP, which is equal to 8,500 kilojoule per hour over COP of 2.5. Okay. W net is equal to, okay, now we have 3,400 kilojoule per hour times 1 hour over 3,600 seconds. 3,600 seconds. 3,600 seconds. R. Okay, equal to 0.94 kilowatt. Joule per second is watt. Next, we have the value network is equal to heat at higher temperature minus heat at the lower temperature. Heat at the higher temperature is equal to W net plus heat at the lower temperature. W net is equal to 3,400 kilojoule per hour plus QL is 8,500 kilojoule per hour. 11,900 kilojoule per hour. Okay, now for the COP, reverse Carnot, which is equal to T sub L over T sub H minus T sub L equal to T sub L is 275 over 303 minus 275. Okay, therefore we have COP of reverse Carnot is 9.82 QH 11.9 kilojoule per hour and W net of 0.94 kilowatt. Okay.